Hi, I'm Toru Tanzaba. Thanks for coming. I'm going to have a series tutorial presentation on charge pump circuits. Please send me email to this address if you have any question. If you have any more interest on this topic, please visit this website. You may find another interesting things. Let's look at the power efficiency of DC-DC charge pump in this tutorial. Please recall that the charge pump input current during steady state. When a charge pump output the I out, which is average output current, then the input current can be expressed by this equation because in the steady state input current from the Vin equal to output current. So similarly, the individual, the driver, to drive each capacitor must input the same amount of current. Because the number of capacitors is now n, then total n plus 1 current pass the charge pump circuit has. As a result, total input current is expressed by this equation. And this doesn't consider any parasitic capacitance component in the circuit. This is just considered the intrinsic term at this point. And this equation can be modeled using a transformer like this. In this figure, the input voltage Vin is multiplied by L plus 1, which appears this point, and this point is considered as V max. And you already know you have the output current, output impedance VMP like this. And with this form, the input current and output current relationship is also given by this model. Let's look at the input power. P is defined by V in times I in. And V in is I in is expressed by this equation, and therefore P in is now expressed by this term. And if you rewrite n plus 1 times V in as V max, then you get this term as well. And P out is, of course, V out times I out. Therefore, if you define the power efficiency by this equation, then you get this, because I out is cancelled out. So let's look at this equation. So we have eta equal V out divided by V max. And if you write the graph between the eta versus V out, and then eta should be the 100%, when the V out is V max. However, at that point, there is no output current because there is no voltage difference between the two nodes of RPMP. So zero output current with eta of 100% is not meaning. Okay, let's introduce power loss with this equation. And then this figure indicates that how we should think about these two. Because power is voltage multiplied by current, so in this case P out is V out multiplied by I out, and P is V max multiplied by I out. And so here's the largest rectangle area indicates the input power, and we have P out in this portion. Therefore, this area indicates power loss. And as the V out increases, I out decreases. Then at the extreme case where I out is 0, then power efficiency goes 1. So this is the exact same condition as the linear regulator. Linear regulator has ideally the same eta versus output voltage condition like this. Okay, let's look at this with a different view. Here are the P out or V out or I out. So we have the V out versus I out has a straight line like this. The X intersection is at V max. V out versus V out, of course, we have a straight line with the slope of 1. Then P out can be given by the multiple of I out and V out, like this. So here's first order curve, another first order curve, but those two multiplies results second order curve like this, and x-axis and x-intersection occurs 0 or at V max like this. Therefore, we have this second order curve, and output power maximized at half of V max. And the middle portion shows P, B, I as a function of V out. We already know I in is a function of V out because I in is proportional to I out like this, and V in is not a function of V out, and therefore P in has this linear line. And ether is given by P out divided by P in, and we already have P out and P in like this. Then, so second order divided on first order result in the first order like this. This is just these two cancelled out, and we have constant term n plus 1. And as a result, we have first order line like this. So this is another view to explain the eta versus V out for the ideal case where there is no plastic capacitance element. Okay, let's look at the actual P out, P in, and ether. And in this tutorial, I just add this bottom plate capacitance, which increases the P loss, and also let's introduce VTH, which is the threshold voltage of diode, and therefore the maximum available voltage is reduced by that factor. When you want the output current at target voltage, even with the finite VTH, then what you have to do? When the VTH increases here, while you want to keep Dmax remain the same, then you have to increase number stage n. If you increase the number stage n, and if you want to keep the output impedance remain the same, then you must increase C at the same rate as n when the clock frequency is constant. And as we have seen before, input current is proportional to I out, and proportional quotient is n plus 1 for the intrinsic term. In addition to that, you must input second term. This second term shows every clock period this additional capacitor must be charged up to be in. And this capacitor, there are n such capacitors in the charge pump circuit, and therefore you have to have additional current component like this. So this n alpha b is C or increases, then input current increases accordingly, and therefore eta must be degraded. So here's the intrinsic term, which has the ideal charge pump circuit had. In addition to that, there is a parasitic element. In this slide, I also add the top right parasitic capacitance component alpha T. And therefore, finally, the total input current is expressed by this equation. And therefore, ether is expressed by this equation as well. This is the actual the case with the finite alpha v. And what is the difference from the ideal case? That is here, I in. We have an offset in terms of this ideal line because of this shift. So this is second term is not a function of V out, and therefore every point you have to add this amount of current, and as a result input power P in increases at the same rate. So to get eta, you have to consider that increase in P in, especially at this point where the output voltage is high. Then there the output power significantly reduced down to 0. Therefore, this point eta goes down to 0 rather than goes up to 1. So in this result, you should consider there is an optimum point to maximize the eta in terms of the output voltage. In addition to alpha v, if you further consider the finite VTH, what happened? So as you see before, when you have to think the finite VTH, you must increase the stage number to get the same output current, V out versus I out curve remain the same. Then the input current increases like this. So I out varies by as a V out. Therefore, the I out also has a steeper curve than the ideal case. So as a result, input power at low voltage condition cases increases further. Therefore, the final eta versus V out curve collapse like this. So this graph shows 3 cases where the ideal case only alpha v considered, and both alpha v and VTH are considered. So as you see, there is the optimum voltage condition and the given parameter. So in contrary, in the ideal case, you get the very high power efficiency when V out is approached to V max. But at that point in actual case, the power efficiency is significantly degraded because there is very little output power, whereas increased input power. As a result, you have optimum V out to get maximum point, and as a result, to have a sufficient power efficiency with charge bond, parasitic element such as alpha B or VTH must be minimized. That's it for this presentation, and thanks.